Alright, so for this video I'm going to be solving some more harder differentiation problems. So if you're preparing for an advanced exam that involves differentiation, this video is right for you. I'll also be giving you tips on how to solve these advanced problems very quickly and easily. Before we start off, it would be better for you to have some knowledge of basic differentiation, things like product rule, quotient rule, a little bit of trigonometry and how logarithms work, just to help you follow along. But even if this is not something that you know very well, I promise this will be a nice video for you. Just make sure you watch till the end. We'll have more and more examples coming up. So let's get started, and if you feel you want to try out any problem along the video, just pause and give it a try, and then you proceed and follow along with the solution. So let's proceed now. For first problem, I want us to begin with this function here, y equals exponent of negative 2 over x times sine of 3x. So we want to find the derivative of this. This is not so advanced, but it's a good one for the start. So as you can see here, we have two functions. We have this function and this function here. So one thing that comes to your mind when you have two functions here is the product rule, especially when they are multiplied together, like in this case. But then, as you can see, this is an exponential function, which in itself could require you to either introduce log on both sides or to use, something like chain rule. So what I'm going to do for this problem is to introduce log on both sides. I guess that will make the problem a little easier. So I'm going to have natural log this side and natural log on this side. So exponent negative 2 over x times sine 3x. Alright, so after introducing natural logarithms, this is very important, we expand this out, because that's going to help us that's the reason we introduce logs anyway, to be able to break down this function into small pieces that are easier to differentiate. So this is the natural log of exponent negative 2 over x plus, you know very well, this, if you have log of AB, this is the same as the log of A plus, I'm using natural logs here, plus the natural log of B. So this is plus the log of sine 3x. Alright, so let's go forward now. I have natural log of y equals, I could just bring this behind here. If I have the log of a to the power b, that's b times log of a. So I'll just use that to bring this power down here. So I have negative 2 divided by x times the natural log of e plus the natural log of sine of 3x. Alright, we're almost there now. We know that the natural log of e is just 1, because that's the antilog of e. So we'll have now the natural log of y equals negative 2 divided by x plus the natural log of sine 3x. Alright, now we are able to take derivatives. This is a little bit easier than what we started with, at least. So finally, the derivative of natural log of y is 1 over y times y prime. Remember, this is kind of an implicit function. So when I take the derivative of natural log of y with respect to x, then I must maintain here y prime. Alright, so what's the derivative of negative 2 over x? Well, negative 2 is a constant. The derivative of 1 over x, so just think of this as x to the power negative 1. So you reduce the power by 1. Drop the power. That's going to be negative, and then reduce the power by 1. So that's negative x squared, okay? So that's negative 1 over x squared. Alright. What's the derivative of natural log of 3x? Well, we take the derivative of 3x, divide by the whole function as it was originally. So what's the derivative of 3x? We take the derivative of the angle, which is 3, and the derivative of sine is cosine. So cosine 3x and then we divide all this by the original function, which was sine of 3x. Okay, so we're almost there. Let's now write our final solution. Y prime equals, okay, I'll just maintain 1 over y here just for a sec. Let me just simplify this a little further. So this is negative, no, that's a negative times a negative, which is positive 2 divided by x squared, plus 3 cosine divided by sine, that is cotangent, so we have cot of 3x. And finally, if we just bring this y from here, we'll have y prime equals 2 over x squared plus 3 cotangent of 3x, all this multiplied by y. But remember, y is this whole function here, and as a rule here, when we take derivatives with respect to a certain variable, then it's always nice if we write our answer in terms of that variable. So our answer should be written in terms of x. I'll now change, write what the value of y is in terms of x. So y prime is 2 over x squared, 2 over x squared plus 3 cotangent of 3x, all this times the value of y, which is exponent negative 2 over x, times the sine of 3x. Alright, so this is a nice one. Let's proceed to another problem. So go to problem number 2. For our second problem, we'll have this function y equals x to the power x. So x to the power x, this is also not so hard, but it's a little bit tricky because we are always, used to differentiating polynomials like y equals x to the power n, where the derivative is simply n x to the power n minus 1. You just drop the power and then reduce the power by 1. Notice that this will only work when the function is a polynomial. So n is just a constant here, 1, 2, 3, 4, and so on. It's just a real number, in other words. But here, y equals x to the power x. X is the variable. It's not a constant. So what do we do for this? Well, we have to make sure this x is not a power. We have to bring it down. We can't differentiate x when it is an exponent. So still, I'm going to introduce log on both sides. And the nicest log to work with here is the natural log. So I introduce natural log on both sides. Alright, there we have it. Using the properties of logs, I have the log of y here equals x times the natural log of x. And then I take derivatives on both sides. So the derivative of this is 1 over y times the derivative of y. By the way, we can also use the dy dx notation if you like that. Alright, so here we have a product of two functions. We have this function and this function here. Just to remind you of the product rule. So according to the product rule, if you have two functions, u and v, so let's say u and v are functions of x, so that's u and v. The derivative of this product is given by u. Just pull that up a little. So it's given by u dv dx plus v du dx. So this is what we call the product rule for differentiation. I'll delete this quickly. Alright, so let's proceed and apply the product rule here. So if I keep x constant, the derivative of natural log of x is 1 over x, plus if I keep this constant, natural log of x, the derivative of x is just 1, so we've got this, so 1 over y times dy dx equals, so this x cancels with this, we have 1 plus the log of x, and finally dy dx is equal to y times 1 plus the natural log of x. So I just substitute for y to complete this. Y is x to the power x times 1 plus the natural log of x. So that's our derivative of x to the power x. Alright, let's proceed. We have a lot more problems to go. So problem number 3. For number 3, let's take y equals sine of x to the power cosine of x. So if you look at this problem here, still the power here is a function of x. So we cannot simply, do this as an ordinary polynomial or the way we usually work with trig functions. I've got to make sure this cosine of x is not a power, so I have to bring it down. So I'm going to do that still using logarithms. So logarithms are actually very useful when you're working with functions in which the power is also a function of x. So we'll introduce the natural log on both sides. So the natural log of sine x to the power cosine of x. Using the properties of logarithms, still I have natural log of y equals cosine of x times the natural log of sine of x. Alright. Okay, so proceeding, the derivative of natural log of y is 1 over y. I'll just use y prime. Okay, so this is a product of two functions. As you can see, we've got this function here. We've also got this function here. So we'll use product rule. Let's begin with this function here. We keep this function constant. So we take the derivative of natural log of sine x. Remember, I'll just remind you here, if you have a function like natural log of f of x, the derivative, say this is y, then the derivative of this is given by, you take the derivative of this function here, divide by the original function f of x. So that's what we are doing here. We take the derivative of sine, which is cosine, divide by the original function sine, which is here. Okay, plus, so we now keep the natural log of sine x as constant, and then we take the derivative of cosine, which is negative sine. Oops. Okay, I'll just put that here, negative sine x. This is not included in the natural log here, so make sure you get that. Okay, so let's try to clean this up a little bit. So 1 over y times y prime equals, so what do we have here? Cos squared divide by sine, or I'll just write this as cos x times cos over sine is cotangent, so cosine x cot of x, plus, now I'll just make this minus times plus, that's a minus, so minus sine x natural log of sine x. By the way, since we are working with sine, with logarithms, I better put absolute sign, because this can only take up positive values, especially if we are to get a real answer, an answer that is a real number. We don't want to get a complex answer here. X is the function, y is a real valued function, we suppose. Okay, so we can now bring this y over to the right hand side. So y prime equals, open a big bracket here, cosine of x cotangent of x minus sine of x natural log of the absolute of the sine of x, all this times y, but we know what y is. Y is sine of x to the power, just raise this up a little, y is sine of x to the power the cosine of x. So it's our final solution. Okay, so let's proceed with another example. That's going to be problem 4. For this problem, we'll have y equals x times 10 to the power sine x. Alright, so let's look at this clearly. As you can see, we have a product of two functions. We've got this function here. We also have this function here. So Intuitively, you would think that you are going to directly apply product rule here since you have a product of two functions. But as you can see, this function here is rather more tricky because the power is a function of x. So we've got to bring this sine x down by any means. So we'll use logarithms to do that. So I'll put log on both sides. So here log of x times 10 to the power sine x. Okay, just simplify this a little. The natural log of y equals, so I can expand this product here as natural log of x plus natural log of 10 to the power sine x. So we have y equals the natural log of x plus sine x times the natural log of 10. Alright, so let's now take derivatives on both sides. So 1 over y times the derivative of y, this equals, if we take the derivative of natural log of x, the derivative of x is 1, the original function is just x here, plus, so look at this, you see natural log of 10 is just a constant, it's a number. You can basically put this on a calculator and get what that is. So this is a constant, so we will not bother differentiating this. We'll just take the derivative of sine x, which is cosine of x, and of course this constant here will remain. So times the natural log of 10. Okay. Alright, so finally we bring our y over to this side. So we have 1 over x plus, I'll just begin with this, that looks nicer, natural log of 10, okay, not so much, natural log of 10 times cosine of x, all this multiplied by y, and then I write what y is. So finally we have the derivative as 1 over x plus the natural log of 10 times cosine of x, all this times y is x times 10 to the power sine x. Alright, this is nice. Let's see, this is problem number 4. So let's take on another problem. This is going to be problem number 5. Okay, number 5. For problem number 5, let's take this function y equals, let's have 3 minus 2 times natural log of x, all this excuse me, all this to the power 3. So there are two ways of doing this, and the main one is actually by using chain rule. So we could let everything inside the bracket here be equal to u, so I can have u to be 3 minus 2 natural log of x, and by doing this I'll have y equals u to the power 3 because all this is u. Now chain rule is very useful when you're dealing with either parametric functions, so what we've formed here by the way are parametric equations, or if you're dealing with a composite function. So as you can see here, we have a composite function. So what you do is to let u to be the inner function so that you can create two parametric equations that are easier to differentiate. Okay, so for this, of course, you can see that dy dx using chain rule is going to be dy du times du dx. So this is so-called chain rule. So what we've got to do here is to find dy du using this function here, and then using this, and then we find du dx from here, and that will be it. So let's go ahead and find dy du. I'll do that here. So using this function, this is a simple polynomial function. The derivative of u with respect to of y with respect to u is 3u squared. You drop the power, reduce the power by 1, so 3u to the power 3 minus 1, which is a 2. Okay, nice. Let's also do du dx. Now As you can see here, we have u equals 2 times the natural log of x. So it's difficult for me to find du dx, but it's easier for me to find, what did I say? Yeah, that's du dx. Okay, that's much easier. I thought that would be dx du, which I would need to flip things later. Anyway, so du dx here is the derivative of 3 is a constant. The derivative of 2 natural log of x, as you can see, negative 2 is a constant. The derivative of natural log of x is 1 over x. We know that already. So this is negative 2 over x. I'll put everything together here. So dy du is 3u squared, and du dx is negative 2 over x. So of course I've got to put back for u. I have to substitute back the value of u in terms of x, but that could depend on how the question is asked. Sometimes they want you to find the derivative in terms of u, sometimes in terms of x. For this problem, we'll put back everything to x. So this is going to be 3, and for u, we'll have 3 minus 2. Okay, so that is 3 minus 2 natural log of x, or all this to the power 2 times negative 2 over x, which actually simplifies pretty nicely to give us, what's this going to be? So negative 2 times 3, that's negative 6 into, so negative 6 divided by x into 3 minus 2 natural log of x squared. So that's our derivative. Alright, so I'll give you a trick though for finding this derivative much faster, especially if you're working with objective type questions. So just do this on a fresh page. So our function is y equals, what's that, 3 minus 2 natural log of x to the power 3. So if you want to solve this very quickly, yes, you can just take this trick here. Every time you have a function like a composite function, let's say f of g, let me just say fg of x. Of course, this is f into g of x. So that's how a composite function looks like. Well, the derivative of this is kind of, you have a technique for doing this much faster. What you do here is, in this case, you reduce the power. So I'll just do this as just we do for polynomials. So you drop this power first, okay? Sorry, you drop the power, and then you keep everything here the same, 3 minus 2 natural log of x, and then you reduce the power by 1, so that's 3 minus 2, sorry, 3 minus 1, which is cosine 2, and then you take the derivative of this function here in the bracket, okay? So the derivative of this, which obviously is negative 2 over x. So you've got negative 6 over x, 3 minus 2 natural log of x squared. So you can see same answer, but very few steps. So don't forget, you drop the power, you reduce the power by 1, just like a polynomial should be, and then you take the derivative of this bracket here, whatever is inside, you take its derivative. Right? Okay, so let's go ahead and do something else here. That was problem number 5. So for problem number 6, let's do the derivative of y equals the square root of x to the power square root of x times the exponent of x squared. Okay, so this looks nice. Y equals root of x to the power root of x times exponent of x squared. Still, you can see you have here the product of two functions, but it would be kind of very huge if you use product rule, because part of the functions here have powers that are functions of x. So that's not good. We have to bring that x down using logs, of course. So let's put logs on both sides. So the log of y equals the log of root x, just make this smaller, root x to the power root x times exponent of x squared. Okay, as you already suspect, we expand this. So we have the natural log of root x to the power root x plus natural log of exponent x squared. Nice. So natural log of y equals, drop this power down here, so you have root x times the natural log of root x plus x squared, the natural log of e, and we know by definition this is equal to 1. So we've got this natural log of y equals root x, natural log of root x plus x squared. So this is kind of a little bit easier to work with now. Okay, let's take derivatives here. So the derivative of natural log of y is 1 over y times y prime equals, so what do we have here? This is a product of two functions which we can actually evaluate since we don't have x as a power. So using product rule, let's keep the root of x as a constant and then take the derivative of this. If we take the derivative of the natural log of root x, its derivative is going to be, remember, you take the derivative of this function inside here, which is 1 over 2 root x, divide by the original function, which is root x. So you'll essentially have 1 over 2 root x times root x. So that's going to be 1 over 2x. So there we have it. Plus, now I keep the natural log of root x constant, and I take the derivative of root x, which again is 1 over 2 root x, plus the derivative of x squared, that's 2x. So let's clean up our answer here. 1 over y times y prime equals, this is got to be root x over 2x. Okay, plus, what do we have here? This is going to be the natural log of root x divided by 2 root x plus 2x, and finally got to bring this y to the right hand side to complete everything. Alright, there we go. So y prime equals, I'll have root x divided by 2x plus the natural log of root x, which is obviously positive, so I have no need of putting there absolute sign, plus 2x. All this is being multiplied by the original function, root x to the power root x times exponent of x squared. Okay, so you could actually multiply these terms inside here so that you have the root x's brought together, but I will not do that. This is fairly okay for this video. Alright, so let's see, this is problem number 6. Got a couple of more problems here, so let's have another. So problem number 7. For problem number 7, so let's do some implicit function here. We have 3x squared plus 2xy plus y squared equals to 2. So we want to find the derivative of y with respect to x. So for this problem here, equals to 2. So for this problem here, of course, as an implicit function, we cannot explicitly make x or y the subject of this equation. So we have to differentiate term-wise. So the derivative of 3x squared is 6x. Of course, you drop this 2 here and then reduce the power by 1. 3 times 2 is 6x, okay? With respect to x, so that's just 6x. For 2xy, so we have two functions here. We have 2x and then we have y. What I like to do for this is to keep 2 as a constant out. So I take the derivative of xy using product rule. So if I keep x constant, the derivative of y is y prime plus, if I keep y constant, the derivative of x is 1. Okay, so come to this, the derivative of y squared, that's 2y with respect to x, so I have to put y prime there. And for 2, the derivative is obviously 0 because 2 is a constant. Next, we collect like terms, so we have 6x plus 2x y prime plus y, plus y plus 2y y prime equals to 0. So let's collect all the terms that have y prime. So we have this here and this here. I'll write these together. 2xy prime plus 2y y prime equals, I take everything else to the right hand side. That's going to be negative y minus 6x. I factorize out y prime from here, so I have 2x plus 2y, which is nice. So this is negative y plus 6x. So finally, I can write derivative y prime as negative y plus 6x. All this divided by 2x plus, just write that as 2 into x plus y, which is nice. Okay, so this is like that. So let's have another. This is problem 7. Let's take problem number 8. Okay, so problem number 8. So I have a lot of problems to choose from here. Let's see. Let's take this. Let's have, we are given that, so we have some functions here, some implicit functions, parametric functions. So x equals t squared, just write that better, t squared plus 2t. And we also have y as t cubed minus 3t. And so what we want to do in this video is to, for this problem, is to find the second derivative of y with respect to x, and we'll do that in terms of t. So we want to find the second derivative of y with respect to x, but in terms of t. So obviously for problems with parametric equations, we have to use the chain rule. So let's go ahead and find the first derivative, dy dx. Using chain rule, of course, that's going to be dy dt times dt dx. Alright, so let's find dy dt from here. That's 3t squared, the derivative of this, 3t squared minus 3. And then let's find dt dx. Now I have t as a function of x, t as a function of x, so it's easier for me to find dx dt instead of dt dx, but of course that's just the inverse of the other, so that will be easier to do. So dx dt is 2t plus 2. Alright, there we go. So we can now find the first derivative already. So dy dx equals, to put this together, so we have dy dt, just use another color, dy dt is 3t squared minus 3 times, so we have dt dx, and we know that dt dx is the same as 1 over dx dt. Okay, so I'm just going to say 1 over dx dt, which is 2t plus 2. Okay, nice. So this can be simplified, of course. So I'm going to have this as 3t squared minus 3. Well, I will not pull out the 3 and 2 because I still have to go ahead and find the second derivative. So I'll just keep this like that. This is going to be 2t plus 2, and that's dy dx. Alright, so this is the first derivative. We are already there, but the question wants us to find the second derivative, and in terms of t. Okay, so let's go ahead and find the second derivative here. This is a little bit trickier. Okay, so to find the second derivative, by definition, the second derivative is the derivative of the first derivative, okay? And we're getting the second derivative with respect to x, so we have to take the derivative of the first derivative with respect to x. Take note of that, okay? But you see here, we cannot take the derivative of this function here with respect to x. Everything would just be 0 because x and t are different variables. So if I take the derivative of this function here with respect to x, everything is going to be 0 because t is treated as a constant in that case. And you can see that it's very difficult for me to replace t with x in this equation here. So what do we do for that? Well, I've got a solution here which I'm now going to show you. So what I'm going to do here is to say, okay, let's take the derivative with respect to t of the first derivative dy dx. Now, it's possible for me to take the derivative with respect to t of the first derivative because, as you can see here, the first derivative is all in terms of t. So I can take the derivative in terms of t. But of course, I want a derivative with respect, I want the second derivative here with respect to x. So to make that happen, I have to multiply this by dt dx. So just think about it this way. Maybe think about it as if this cancels with this. Of course, that's mathematically not true. But if that were true, then you can see that we would have d dx of dy dx, which is the exact thing that we wanted to find here. Okay, so I'll remove this because it's absolutely not true that we cancel this out, but you know, just to show you how this kind of comes out. So I will now do that. So I take the derivative with respect to t of the first derivative. What's the first derivative? We have 3t squared minus 3 divided by 2t plus 2, and I will multiply this by dt dx, which obviously we already calculated. So dt dx, we have dx dt, so we can easily find dt dx. Okay, so let's go ahead and take this derivative here. We will use quotient rule. So I will show you what quotient rule looks like. If you have u and v as functions of x, let's say a quotient of u and v like this, the derivative of u and v with respect to x is given by v du dx minus u dv dx, all this divided by v squared. So notice the order here matters. You've got to begin with v and then minus u because this is a subtraction. I mean, subtraction is not commutative, and you have to divide by v squared here. Okay, so let's do it here. So this is the u function and this is the v function, just to compare that. So you have v, which is 2t plus 2 times du dx, which is in this case 3, not 3 actually, 6t, because the derivative of 3t squared is 6t. The derivative of 3 is 0, so, okay, minus u, which is, I'm just following this expression here. So u is 3t squared minus 3 times dv dx. So if I take the derivative of this denominator here, that's just going to be a 2. Divide all this by v squared, which is 2t plus 2. I'll have this squared. Okay, I'll now multiply this by dt dx, which is 1 divided by, I'll just refer to this again. So dx dt is 2t plus 2. So this is going to be 1 over 2t plus 2, which is what we have here, 2t plus 2. Okay, nice. So we're almost there. Just a few steps to simplify this. Okay, So our second derivative is, so we have 60. Let me just pull out a 2 here and then multiply that by 6. So I have 12 into, so 12t, sorry, into 2, not 2t, so that's t plus 1 minus 2 into 3. Okay, I'll just pull out a 3 to multiply this, which gives me 6 into t squared minus 1. Okay, that's nice. All this is divided by 2t plus 2. Of course, this is squared, this is to the power 1, so that will become to the power 3. Now, of course, you can go ahead and simplify the numerator here. It's always a nice practice to simplify expressions in math. So let's see what we've got here. So we have, of course, this is the same as, this can be written as t plus 1 into t minus 1. So I think we've got a common factor here of 6 t plus 1. Let's see if we factorize out 6 here. So we'll remain with 2t minus, so factorized out a 6, and then we have only t plus 1 or t minus 1, which if I just enter this, that will become minus t plus 1. So it turns out that I just have t here plus 1. Okay, nice. All this is divided by 2t plus 2 to the power 3, which, okay, this simplifies further to 6 into t plus 1 squared, divide by, okay, what we have down here, that's 2t plus 2 to the power 3. Okay, so this is the second derivative of y with respect to x, but in terms of t, as the question required us to evaluate. So there we have it, problem number 8. Okay, so let's move on to another problem. So this is going to be number 9. For problem number 9, let's have this function here, y equals x to the power natural log of x times sec of x to the power 3x. Okay, this is nice. X to the power natural log of x times the sec of 3x. Again, we have a product of two functions here, but for both functions, the power is also a function of x, which is not something that we want. So I'm going to introduce natural logs on both sides to try and bring these x's down, just to make everything nicer to work with. So the natural log of y equals the natural log of x to the power natural log of x here, okay, times the sec of x to the power 3x. We'll now expand this, so the natural log of y equals natural log of x to the power natural log of x. It's kind of nice. Plus, the natural log of sec x to the power 3x. Okay, I'll now bring these down. That's why we actually used logarithms here. So I bring this down, so I have natural log of x times natural log of x, okay, plus 3x natural log of sec of x, okay, that has to be a positive number. So just to simplify this further, we have this as natural log of x squared plus 3x natural log of sec of x. Okay, so now that we don't have any power as x, we can start taking derivatives. Alright, so the derivative of natural log of y, that's 1 over y times y prime. The derivative of natural log of x, all this squared, I'll use a shortcut, that I showed you already. So drop this power down here and then reduce this power by 1. So natural log of x to the power 1 times the derivative of this bracket, which is 1 over x. So just put that here as divided by x. Okay, plus I'll use product rule here. So the derivative of 3x, so I'll keep 3x constant first. I take the derivative of the natural log of sec. So remember, I take the derivative over the original function. So the derivative of sec is sec x tan x. The original function here, of course, was sec x. Okay, second part here, I will now keep the natural log of sec x as a constant. I take the derivative of 3x, which is just a 3. We're almost there. So I have 1 over y. So alright, I'll just bring that y over to the right hand side after simplifying here. Just use another colors because I have too many things here. Okay, so I have 2 over x, just extend that here, 2 over x, natural log of x plus, so sec x cancels out here, so I have 3x tan x plus 3 times the natural log of sec of x. All this is being multiplied by y, remember this y here. So I can now finally write my solution as y prime equals 2 over x natural log of x plus 3x tan x. Oops. So that's 3x tan x plus 3 natural log of sec x. All this multiplied by y. Remember what y is? Y is x to the power x times, x to the power natural log of x times the sec x to the power 3x. So that's our final solution for this problem. Okay, let me see what this is. This is problem number 9. So we'll proceed with problem number 10. Okay, sorry. So that's problem number 10. Problem number 10, let's take the derivative of this function here. Y equals, let's see, what do I have? Arctan of x divided by 1 minus x squared. Arctan of x divided by 1 minus x squared. So let's begin by introducing tan on both sides, because arctan is, it's not a nice thing to work with for derivatives. So I'll introduce tan on both sides, and this works for all inverse trigonometric functions. Begin by, eliminating the inverse function here. So, let me just use red color here. So tan of y equals tan of the arctan of x divided by 1 minus x squared. So that becomes tan of y equals, so the tan of arctan is going to be, x divided by 1 minus x squared. That's the inverse function. So when it acts on it, we have this. Okay, so by the way, we can interpret this geometrically as, if you have a triangle, a right angled triangle, of course, with an angle y, so you have the opposite over the adjacent. That's by definition what tangent is. Just rub off this. So the opposite to this angle is going to be x, and the adjacent is 1 minus x squared. So by Pythagoras theorem, the hypotenuse is going to be 1 minus x squared plus, what's that going to be, plus x squared, all this under the square root. If you expand this, of course, you've got to have 1 minus 2x squared plus x to the power 4 plus x squared, which is going to be, so I collect like terms here, that's 1 minus x squared plus x to the power 4. So that's what we have here, 1 minus x squared plus x to the power 4. Oops, just make this better, x squared plus x to the power 4. Okay, that's what we have. You know, it may be useful at one point. Okay, so what do I do next? I take derivatives now for this function here. The derivative of tan y, the derivative of tan, first of all, is sec squared. So we have sec squared y, but of course times y prime, because we are taking derivatives with respect to x. For this part here, using quotient rule, I'll let this to be u and this to be v. Remember, according to the quotient rule, I actually did this already. So if you have a quotient of two functions like u over v, so this is going to be u v prime minus, that's v u prime minus u v prime over v squared. Okay, so just take this off. So using the quotient rule, we'll have v, which is 1 minus x squared, times u prime, which is going to be a 1 minus, so we have u, which is x, times v prime, that's going to be negative 2x. All this divided by v squared, 1 minus x squared squared, which is, let's see, this is 1 minus x squared minus, so this is actually plus, negative times negative, this is 2x squared, divide by 1 minus x squared squared, which simplifies to 1 minus x squared, divide by 1 minus x squared squared. Okay, I've got that. Okay, yeah, so this is 1 over 1 minus x squared. Okay, don't forget, this is just one side of it. We left out this, so I now bring everything back together. So this is sec squared y times y prime equals 1 over 1 minus x squared. Alright, so I will now make y prime the subject of the formula. So I have 1 over 1 minus x squared times 1 over sec squared y. But of course 1 over, just use another color here, 1 over sec squared y is the same as cosine squared of y. So I'll just replace this with cosine squared. So this is 1 over 1 minus x squared times cosine squared of y. Now, do we know what cosine squared is? Yes, somehow we do. If you come back here, we can tell what cosine is from this triangle here. Cosine is by definition the adjacent, which is this, divided by the hypotenuse, which is this. Okay, so I'll take you back to down here. Okay, so y prime equals, of course this is the same as cosine squared y over 1 minus x squared. So for cosine squared, I'll replace that with, what's that? We had the adjacent 1 minus x squared divided by the hypotenuse, which is the square root of 1 minus x squared plus x to the power 4. And of course all this is squared, and then we have down here 1 minus x squared, this here. Okay, so finally we have y prime equals, I'll just expand this quickly, I'll skip some steps here. This is going to be squared, so it cancels with one of these here, so we'll just have 1 minus x squared on top, and for the denominator we'll just have 1 minus x squared plus x to the power 4, because we've got this square root here. When I square it out, just remain with this. Okay, so this is the derivative of that's the derivative of the tangent of x divided by 1 over x divided by 1 minus x squared, and that's our problem number 10. Okay, I still have a lot of problems, but I feel like I should stop here, not to make this video long. I think I'll make a follow-up video, like part 2 of this, with more harder advanced derivatives. So I'll see you in that video. If you find this helpful, please give me a thumbs up. By the way, if you have not subscribed to the channel, please do so. I produce content almost every 2 days on interesting problems in physics and math, full courses of different topics, and I love to simplify physics and math to make it understandable to every student. That's at least my goal. So I would really appreciate if you support me by subscribing. If you can, become a channel member. There are links in the description where you can join. You can support me on Patreon. Alright, so enough of this video. I'll see you in part 2. Thanks for watching. Have a good time.